looking at logarithms. Now, to understand what logarithms are, let me just explain about a certain function that you might already be familiar with. Suppose we had a function like this. Now that's an exponential function and pretty easy to work with. We simply plug in different values of x, work out the corresponding values of y. No big deal. But suppose you wanted to try to figure out the inverse of this particular function. Well, how would we find the inverse of this function? Well, we would put an x where the y is, and we'd put a y where the x is. So we get a function that looks like this. Now, that is the inverse, but how do we write this now as y equals? That's where we run into a bit of a problem. We really can't. And so, another way of writing this exact relationship is the idea of logarithms. A same statement as saying x equals 10 to the y is to write it this way. Y equals log base 10 of x. And this is saying precisely the same thing as this is. Now this is what we would call logarithmic form, and this is exponential form. But really important, and I can't stress it enough, we're really saying the same thing with these two statements. And sometimes this one is more desirable and easier to understand, easier to work with, and sometimes it's easier to go to this form. So, let's now look at our new function, this logarithm function here. There's certain parts of this function that we have names for. This little 10 down here, well, that was the base of this power. Okay? And so this is a logarithm to base 10. So it's still called a base. And this particular logarithm, when it's base 10, is usually not written. The 10 is usually left off. So we usually write it like so. Y equals log x. And this is so commonly used that it's called the common logarithm. One more thing about logarithms that we should talk about, very important, is their domain and range. Well, let's look at this little function here and try to analyze its domain and range. Now, here it's probably easier to go to the exponential version of it to try to analyze it. Let's face it, we're not really that comfortable with this form yet. For most of us, it would be new. So let's look at what domain and range would be in terms of this exponential. Okay, let's start off with looking perhaps at the range. Because their roles are kind of reversed, it's actually easier to start by looking at y and then sort of analyzing the x's. So we're going to look at the range first, or the y values. What kind of numbers could y be? Could y be a negative number? Well, I don't see a problem with that. Let me just analyze that. Make a little room here. Suppose we did try a negative number, something like negative 1. Is 10 to the negative 1 okay? Yeah, that's just 1 over 10 to the positive 1, 1/10. So negative numbers are all right. 0 is okay. 10 to the 0 is just going to be 1, so 0 gets a green light. And positive numbers are okay, something like 10 to the 1, well, that's just 10. That works too. So as far as the range or the y values are concerned, we see all real numbers being pretty easy to put in for y. But what kind of corresponding domain are we getting? What kind of x values are we now looking at? Well, something you should notice with these little exemplars here, where I plugged in a negative y and a 0 and a positive y, all these numbers here have something in common. They're all positive numbers for a start, and they're also never seemingly 0. No matter what numbers we seem to pick as the exponent, doesn't seem we can make 10 to the anything turn to 0. And if you think about it, it's very true. I mean, let's say I tried to, might do a little bit of an analysis here, say to myself, well, you know, what if I thought maybe I could 10 to something equal 0? Is that possible? And you would try various negative numbers and realize no. You might try 0 itself, realize that'll give you 1. And try various positive numbers, no. So what we're getting here is, for the domain, all of the x values are going to be greater than 0. They're going to be positive numbers, and they're not going to include 0. So that's a very important little thing about domain and range when we look at logarithmic functions. Something that will really help, of course, is when we look at the graph later on. And I'm going to save that for a different lesson because that's a pretty big topic. So that's something that, when the time comes, we'll get to it. Let me just do some examples now of logarithms in action. So for our first example, we're going to try and solve this little guy here. Log base 2 of 8. So what we're trying to do is say, well, log of 8 base 2, what would that equal? Now, don't go rush into your calculator, because on your calculator, this button here, where it says log, that is log base 10. That's your common logarithm. So that's not going to be of a great assistance to us here where we have base 2. So the calculator is useful, and we'll see very useful later on, but right now we're just going to have to go with our brains. So what do? Well, here's what we do. We remember maybe the logarithmic form doesn't help me, but the exponential form might. So suppose I just said, I don't know what this is. Now, let's have a look at what the logarithmic corresponding exponential sort of counterparts, what they look like, and see if we can guide our way through it. We saw in the original, it looked like this. X equals 10 to the y, and the logarithmic version of that is y equals log base 10 of x. So that's going to help us guide us what goes where as far as the exponential. So I'm going to look at this thing now and say, well, let's see. Here we have an 8 and a 2 and then an unknown. Now what goes where? Well, let's see. Where did the 10 go when we went over to here? Because here's what we've got. We've got log base 2 of 8 and an unknown. That's what we have. Okay, so what goes where? We're going to this version here. Well, let's see. The 2 is acting like the 10, so it becomes the base here. So now we want to put a base of 2. What would be next? The 8 is acting like the x, and the x goes to the other side, so we put the 8 there. And the unknown is behaving like the y, and it becomes the exponent up here. So let's see, does that help us answer the question? 2 to what exponent equals 8? I think you know the answer. 3 is correct. So not a very difficult question once we were able to make this kind of comparison. Now here's a kind of a quick way that works for me. When I look at logarithmic statements, I just go like this. I look at the base and I go 2 to this exponent equals this number here. Okay, so maybe that was a little quick. Let me do it again for you. 2 to this exponent equals this number here. And you'll find that's a very speedy way rather than to have to go through this rather painstaking process every time. Let me just show you with the next example. So, let's take log, and we'll go with base 4 and 1/16. What does that equal? Well, here's my speedy method in action. 4 to what exponent equals 1/16. So here's what I'm thinking to myself. 4 to what exponent gives me 1/16? Now, clearly, to make a fraction, we're going to have to go to a negative exponent, and I think most of you would recognize that that would have to be -2. 4 to the -2 equals 1/16. Right on. Okay. Now, a couple more things about the logarithmic function itself. Let's get a little bit of room here. Okay. The idea of the logarithmic function itself, one more thing I haven't discussed. And that is, what about the base? What about b here is the way I've written it? Anything about b that might be important to us? Well, yes. Remember, the exponential version of this is b to the y equals x. Okay? So to make a bit of an analysis here, there's certain restrictions on b. Just as we saw with our domain and range, there were certain restrictions or behaviors for the x and the y. It turns out like this. For b, in order for b to cause this to be a function, b has to be greater than 0. So it has to be a positive number. Okay? If it's a negative number, what happens is, as the y's change, this thing oscillates from a positive to a negative. And so it kind of oscillates up and down, and it just doesn't behave the way we like a function to behave. Another restriction on b is that it cannot equal 1. The reason it cannot equal 1 is, once again, if you put a 1 in here, 1 to the y equals x, and you analyze it, you will discover you get a vertical line. And a vertical line is not a function. So we have to make that restriction on b. So here's, when we look at a logarithmic function, all of the restrictions. First of all, we saw that our domain, or x's, have to be greater than 0. And we saw that y is all real numbers. So here's what we have. We have domain, all positive numbers, greater than 0. Y, all numbers. And the base behaves very much like the domain, except that we have to exclude 1. Okay. All right. Now that we've set the stage, let's look at some more examples. The next example, pretty quick and easy. Again, using my speed method, 2 to what exponent equals 64? Most of that you can probably solve pretty quick by inspection. I think you'd realize that has to be a 6. You'd be right. Okay, so we're now blasting along. Doing pretty well. Now how about this funny looking one? Log of 4 to the 5th base 4. Now again, the speed method unravels it quickly. 4 to what exponent equals all of this, which is 4 to the 5th. So 4 to what exponent equals 4 to the 5th? I think 5. Not too bad. Okay. All right. Let's move on to the next thing. All right. Even though I said I was going to save the graphing stuff for later, I'm just going to show you a little bit, because I really think you're probably very curious as to what a graph of a logarithm might look like. So we're just going to take a very simplistic look at one graph. And that's all we're going to do. So don't worry being disappointed. But we are going to look at just one little sneak peek at a graph. So we're going to try and make some kind of sense of a graph like this. How would I graph something like that? Well, let's go to the exponential version of this, which is 2 to the y equals x. Okay? And as far as our graphing tools right now, we're just going to use a few points on a table of values and just get a sort of a rough sketch. So here we go with our table of values. And you notice to create my table, I'm using this exponential version of this logarithmic function. Why? Because this I understand. This, it's all sort of jumbled and new. So I'm going with what I know. Okay, what can we do? Well, it's easiest if you put in a few y's first and then find the corresponding x's. So I'm going to put in a negative y value, something like -1, maybe a 0 for y, maybe a 1, and if I want to get fancy, maybe a 2, something like that. So I'll develop a few points. If I put 2 to the -1, 2 to the -1, what do I get? Well, I get 1 over 2 to the +1, or 1/2. If I put in a 0 for the y, I get 2 to the 0. Well, that's going to be 1. If I put in a 1, well, these are getting pretty good. 2 to the 1, that's a 2. And lastly, I put in a 2 for my exponent. 2 squared equals 4. All right. Very strange when you put the y's in and find the corresponding x's, because usually we're so used to working from x's. And anyway. Okay, let's make a little room. Make a little picture here. What do we got? Well, let's get a little grid going. Okay, let's see. We got 1/2 to the right corresponds to -1. Okay, so a 1/2 to the right corresponds to -1. And 1 to the right corresponds to 0. 2 to the right corresponds to 1. And 1, 2, 3, 4 to the right corresponds to 2. Thought I wasn't going to make it, but I'm okay. All right, so there's our points. So here's the kind of graph we're going to get. If we kind of draw some of these points, it kind of starts to climb, but it levels off a little bit, but never quite entirely. And then this side goes down like so. So a few key important ingredients here. What we have here is this graph gets closer and closer and closer to the y-axis, but never touching, which means we have this vertical asymptote at the y-axis. And over on this side, it keeps climbing and climbing and climbing and climbing. There's our graph. And that's all we're going to do. I promised you we'd save more of the graphing stuff for another lesson. Okay, I have one last example I want to talk about where we see logarithms used. And that's, you have to understand how the Richter scale works. The Richter scale is the way we measure power of earthquakes or seismic activity. And here's how the Richter scale works. If we say that we have a Richter reading of 1 on the Richter scale, we're going to say that it represents a power of 10 to the 1. If we go up the Richter scale and say we have an earthquake with a 2.0 on the Richter scale, that means the power is 10 to the 2. And if we go up to 3 on the Richter scale, that means the power is 10 to the 3, and so on. Now what you can see is happening here is as you go from one increment to the next on the Richter scale, the power is 10 times as much as the previous setting. Okay? So if we wanted to compare some earthquakes, for example, we have to understand that it's not a kind of a linear comparison, but it is this exponential or multiples of 10. It's sort of, well, not multiples of 10, but sort of tenfold growth as you go up the Richter scale. A simple way to compare would be, suppose we had a quake somewhere that measured a 7.3 on the Richter scale, and say we had some other quake that measured 5. I'm going to go back and change this, otherwise my numbers don't work. 7.4, and then the second quake is 5.3. Now suppose I want to know how much more powerful is this first quake. Okay? So I'm going to take the bigger quake here, and its power is 10 to the 7.4. That's how powerful this first quake is. I'm going to divide that by the smaller quake to see how many of these smaller quakes fit into or divide into the larger quake, to see how many more times powerful the bigger quake is. Well, this would be pretty easy to do on your calculator. If you want to, you can go ahead and subtract the exponents and get 10 to the 2.1, and that rounds to approximately 126 times as powerful. So it's very impressive. Yeah. Okay. Not a whole lot to do with logarithms directly, but it is something you have to know in a Math 12 course, is how to compare earthquakes on the Richter scale. So that's where we're going to stop for today. We're going to talk a little bit more about logarithms next time, but for now,